All right. Hi, everybody. My name is Garett Graham. I'm a research associate with the North Carolina Institute for Climate Studies in Asheville, North Carolina. And I've been working closely with Ronnie Leeper over the last basically two and a half years off and on trying to develop some machine learning tools to quality control soil and moisture observations from the US Climate Reference Network from the soil moisture sensors there. So as I'm talking to a room of soil moisture experts, you all are going to be familiar with diagrams like this or figures like this. I tried to build this presentation as kind of a big tent presentation because I don't know what everybody's backgrounds are. And my background is certainly not soil moisture, which is why I've been relying heavily on working closely with Ronnie on this. It's been a true collaboration over the past couple of years. And we also, I'd be amiss if I didn't mention that we've had two different interns who have been wonderful, Jeff Alexander and Vivek Sudhakar, who have been helping us on this. So basic problem, I'm sure all of you are very familiar with this. I've already heard quality control, QCing. I've heard that thrown around a lot today, but these sensor networks bring in a lot of data, and that data is sometimes error prone. These sensors are sometimes error prone. And as you can see over there on the right, in the figure on the right, there's a lot of data that comes in that needs to be checked manually sometimes. It can't all be done in an automated fashion, and that consumes a lot of time. And so machine learning models are great or have been proven in other instances to be great at finding errors or anomalous data and doing classification and anomaly detection, which are two different things. I'm going to be talking mostly about anomaly classification here. And so we decided to give it a shot and see if we could develop a machine learning model that would allow humans to do what they're best at, which is think creatively and analytically about problems rather than having to manually QC data for hours and hours. So in the USCRN soil moisture network, there's about 11 different classes of anomalies or errors that operators of the network were going through and manually flagging for years. And so this is one of the unique things about this data set is that a lot of data sets, a lot of machine learning data sets are built, especially for classification problems, they're labeled specifically for machine learners. This one was not. This one was labeled for human users. And then afterwards, we were trying to adapt those labels to use by a machine learning model. So in order to make the problem a little bit easier, just to see if the idea was viable, we subsetted the data set down to just the two dominant types of errors or anomalies, which are spikes, which you can see a few examples of highlighted over here with red, and then noise. And both of these occurred by far the most out of all the 11 different classes. And so we turned this into a multi-class classification problem with 3 different classes, represented by the 3 different colors in this, this pie chart over here. Green is normal data, red is noise, and then orange or yellow is spikes. So you can see from the chart over there on the right that this already shows another distinct thing about this data set, this sensor network. And if you all are interested in using a tool, a machine learning model like this later, you'll probably find the same thing in your sensor networks. Hopefully, you want to find, ideally you're finding that anomalies are quite rare. But what that does is for the machine learners, that creates a very specific type of problem called a class imbalance. And that comes with its own unique challenges for designing machine learning models that are actually effective at detecting anomalies. So actually going back to this just for a moment, a little bit more on that. Machine learning models, they require a lot of data. The more data you have, the better. The more examples of anomalies you have, the better. But the thing is ideally, a sensor network has very few anomalies. So you end up in this competition between a good sensor network and a machine learner that has enough training data to actually recognize what anomalies look like. So it ends up in this competition, and you have to kind of make up with sensor networks. You kind of have to make with good ones. You have to make up for that. The machine learning operator or trainer or like the person that's programming it has to actually make up for that with some judicious choices about how you train the machine learning models. So at a very high level, we've been using 2 different general classes of machine learning models. I'm going to go over the Most of the results are going to be from the classes on the left. And those are tree-based models. So tree-based models, they use decision trees, but they use a lot of them. They use them, they combine them in various forms of like different ways. Some ways have advantages for certain types of problems. Generally, if you're using random forests or XGBoost, those are the two most common ones, you're going to be on a good track. The advantage of decision tree classifiers is that they're very versatile and they can be trained on pretty generic computing hardware. So you all could probably train them on your laptops. I'm seeing a lot of laptops that could probably run the training for a lot of these decision tree classification algorithms. The one disadvantage of tree-based models is that they really can't take advantage of the time series nature of your data. So they're just looking at single time slices. So then it's incumbent on the machine learning like practitioner, the coder, it's incumbent on you to actually come up with a way to cleverly feed the data in if you want to try to incorporate maybe some time series data. So you can so for instance, maybe incorporating a rolling average, maybe incorporating some sort of standardization within a certain window, stuff like that. So there's ways to get around that a little bit, but they really, tree-based learners are literally just looking at single snapshots of time when it comes down to it. So you just have to be aware of that. So there's a limitation. Advantage, you can train them on a laptop. Disadvantage, can't look at time series very well. On the right-hand side, you'll probably have heard a lot about deep learners or deep learning algorithms. These are just more complicated versions of neural networks. Neural networks are more complicated versions of linear regression or logarithmic regression. So recurrent neural networks, deep learning networks are one form, or recurrent neural networks are one form of deep learning networks where they can actually remember the history. For a brief window, they can remember a little bit of time of the history of the time series that you're feeding it. So that makes them really good for time series data. But the disadvantage is that if you try to train these on a CPU, on just generic, generic computing hardware, it's going to take a really long time. So it behooves you to have access to a GPU for training them. Once you have a machine learning model trained, you can actually run it on a CPU, but Amazon Web Services in this case would be your friend. You could, for about $20, you could rent out an EC2 instance on Amazon Web Services that has a GPU attached. That'd be for about a day. You could do your training, export the model, use it afterwards. They're also more complicated to train. That's the other problem, or disadvantage, I should say. So results from the decision tree based anomaly classifiers. So they did pretty well. They required a lot of pre-processing. We had to really think about how we were going to pre-process the data. They did over here on the left, you can see that they were pretty good at recognizing what normal data looked like and not misassigning it to either of the anomaly classes we were looking at. They did pretty well with spikes and they did really well with noise, or a lot better with noise. Over here on the, so this is kind of a representation of a confusion matrix. Over here on the right, though, you can see the time series data. So the shaded background is where the manual QC was saying, hey, there are anomalies here. The red dots are the points that were correctly identified by the machine learning algorithm, by the tree-based methods as being anomalous. So you can see that over here and on the left-hand panel, the left-hand time series, you can see some of those red dots out kind of on the right-hand side in the black. Those are false positives, but you can see over on the right-hand side, all the red dots that are clustered in the red shaded background, those are true positives. So work pretty well in these instances. So the disadvantage of this, one of the limitations here that might not be obvious right off the bat though, is that remember that most of our data is normal data. We're looking for needles in a haystack. So because we've got so much normal data, so much green data there, if you mislabel even some of that data as anomalous, you're still sort of condemning a human QCer to spending a lot of time going through and manually picking out, okay, that truly is an anomaly. No, this is just mislabeled normal data. There's fewer anomalies, so mislabeled data there is easier to check, but we were pretty interested, Ronnie and I were pretty interested in sort of pushing this a little bit further and seeing if, if there was a way that we could really clear up and avoid mislabeling some of this data with maybe a more powerful machine learner. The other thing was that this didn't give us, we decided to go ahead and move to more powerful machine learners before incorporating all of the 8 other classes of anomalies, because some of those classes were exceedingly rare, just a few dozen examples across the network. Another thing that we tried, so this is what I've been talking about, is supervised machine learning so far, where you're labeling, you're feeding it an anomalous point, and you're like, hey, this is an anomalous point. This is a spike, this is an example of noisy data. You can also do unsupervised machine learning, where you just feed it normal data and you just train a machine learning algorithm to see what normal looks like. You're like, hey, this is a bunch of normal data. And then you start feeding it, you start testing it on abnormal data and see if it can recognize what abnormal data looks like. That's unsupervised machine learning. It's kind of trying to train it for one of these things is not like the other. For non-deep learners, kind of state of the art there is a tree-based method called isolation forest. And we tried that and it actually did not work very well. So I'm not sure if anybody else around, like in the room, has tried isolation forest on their sensor networks. If you have, I'd love to talk to you afterwards, because I'd be very interested to hear what you've done. So tree-based learners, great, very effective, but with limitations. So we've moved on to trying deep neural networks. We're in the initial phases of using them and training them. So this is kind of a public service announcement slide for if you guys start using these, what to look for, things to watch out for. So on the left-hand side, we have a confusion matrix that represents the results of how a deep neural network would generalize to unseen data. With confusion matrices, what you're looking for, you're always looking for bright colors down the diagonal. So this one over on the left looks great. Turns out after some digging though, we were a little suspicious. Turns out after digging, our intern who was working on this had made a mistake in his cross-validation strategy. And I hadn't caught that before he had run it. And so we saw it, and basically what was happening is there was information leakage, and that was allowing the machine learner to kind of cheat. And so that's one thing to look out for. Another thing to look out for is over here on the right. So we corrected that information leakage, and we actually made things really strict for the machine learner and the deep neural network instead. So this represents results on data that the machine learner has been trained on, that the deep learner has been trained on. You would expect there, you should actually expect to see a bright diagonal. Instead, you're just seeing a single column, which just means that the deep learner is only guessing. Anytime it sees any data, it just guesses the dominant class, which is normal data. It's just saying, hey, the best way I can get the best score is just by guessing that the data is normal. Don't be, if you end up seeing results like that, don't be discouraged. That just means that your loss function or maybe your network architecture or something like that isn't quite correct yet. You just got to keep on working to get it. So yeah, so if you all have any questions, if you think any of this could be useful to you, please let me know or let Ronnie know. We'd be happy to help.
Thanks, Garrett. Do we have any questions from the audience?
A very interesting presentation. I'm really curious about you mentioned the cross-validation strategy wasn't correct. Could you elaborate on that a little bit with your previous slide?
Yeah, absolutely. So with time series data is highly autocorrelated. If you have time point 1, time point 2, time point 3, time point 1 and 2 are really similar. Time point 2 and 3 are really similar. And as you get further away in history, they become less similar. What was happening is, so you want to make sure that when you're training a machine learner, that you're training it on data that is temporally separated from the data that you're going to test it on. Because you want to train it on one set of data and then test it on an unseen set of data to make sure that it's going to, your model is going to generalize to, the real world, quote unquote. In this case, there was there's a shuffling operation, which is very normal in most machine learning training when you're not dealing with time series. There's a shuffling operation that we thought we had disabled that was happening in the background. It took some digging. We found out that the shuffling operation is happening in this cross-validation strategy. So
Just quickly, did you consider autoencoders?
we've actually tried a semi-supervised approach with autoencoders before, or we started dabbling with that, but we decided that it would be a better idea to just try to replicate and sort of benchmark the tree like classification deep learners that are classifying and benchmark them against the tree-based methods that we've been using before we move on to a more complex, on to a slightly more complex machine learning algorithm that we don't have an analog for in sort of in a non-deep learning setting. Does that make sense? Okay. But we'd really like to try them.
Thanks, Garrett.